Okay, so we're going to look at the actual execution of some specific instructions using the different addressing modes. Just so we can see what happens in the fetch execute cycle when we get to that execute stage. Because we just tend to say execute as one step, but there's multiple steps. Right, in order to follow this through, what we're going to do is we're going to look at the contents of the registers. So I'm going to write out what the fetch execute steps are. And obviously the first bit's going to be the same every time. It's the after we've done the decode that it starts to change. But we're going to do like a little trace table. So what you will probably want to do, if you're going to follow along with this, is just write yourself up some headings. PC, what are the registers will change when we execute instructions? MAR, MDR. What logically in the fetch execute cycle would we come across? Yeah, that's how I want you to try and remember it, because you were going that way. You were like, oh, right, okay, we meet. When do we meet them? And then the accumulator. Okay, they're the registers that are affected in general, not always the accumulator, but in general. And we're just going to keep track. And remember, when we're tracing an algorithm, which effectively that's what the fetch execute cycle is. We just, whenever something changes, we just write down another number. So if we want to know what the current value is, all we need to do is look at the bottom of each column. Okay? But obviously I'm just going to rub those out. Don't write those numbers. Right, okay, so we need an instruction. So the first one we're going to look at, and the first addressing mode we're going to look at, is where we supply a value directly. So let's just have a quick recap. A machine code instruction has got two parts. What are those two parts?
Operator and operand.
We don't call it operator, that's maths.
Opcode.
Thank you. Anonymous 1. And Anonymous 2. It was a dual effort. Could be. You could say combined duo Anonymous 3.
Me?
No, Anonymous 1 and 2. 1 plus 2.
Oh, okay.
If I was doing it
Wouldn't that be a whole
mathematically.
new person? Anonymous three?
No, it's more like a team.
Oh, okay.
Right, so we have the operation code, which people who are cool call it an opcode. Other people call it an operation code because they're not as cool. And we have an operand. Now, I wasn't referring to Anonymous 1. Might have been Anonymous 2. I can't remember who said it now. I told you I'm going to amuse myself with this. If I've got to do this, I'm going to do it amusing. Right, so we've got the operation code, which is the actual instruction. And then we've got the operand, which is the information the instruction needs. Okay? But the operand has got two parts. What are the two parts that comprise the operand?
The address.
No. The addressing mode. Remember, the addressing mode is how to interpret the operand. So the addressing mode says, right, what actually is the operand got in it? And the other part is the actual, what is that data then? What data have we got? Okay. If you look at a proper machine code instruction, and we will look at some later on, and I was elucidating to this the other day when I was showing you the instruction manual for Z80, I think it was. You have a few bits in the operand are dedicated to the address mode. So if you had 3 bits, how many different address modes could you specify? If you had 3 bits.
Is it 2's complement?
No, it's pure binary. What do we call, what's the proper name for pure binary? Unsigned. 8. Thank you, Anonymous 2. Were you Anonymous 2 last time?
I don't think you
I
can
thought you had anything.
You can't say people's names. Can't say people's names. Are you anonymous 4?
From the
I'll
start.
be anonymous.
Right, anonymous 4.
Take 2.
Well done, anonymous 4. Yeah, 8. Sort of detracts from the 8 that we were trying to get to there, doesn't it? Right, yeah, 8. With 3 bits, you can represent 8 different things. So if you dedicate 3 bits, you can have 8 different addressing modes. If you only had 2 bits, you could only have 4 addressing modes, couldn't you? So you'd put like a 00, an 01, 10, and 11, and that would be how you distinguish what addressing mode. So the rest of the operand is the thing that we want to interpret. Okay? Right. We're not going to write in machine code. We're going to use assembly language. So what assembly language gives us is an easier way of remembering the instructions. There is a 1-to-1 mapping between assembly language instructions and machine code instructions. So when I write something like, so I'm just going to rub that out because it's in my way now. But I keep doing this. When I write an assembly language instruction, I'm just basically writing machine code in a human readable form. So I might write something like this. So at memory location 150, I might have LDA hash 6. Okay. Now, the symbols that are used to represent the addressing modes change between CPUs, and the CPU manufacturer generally specifies the assembly language. But we can look at this and we can say this part is the opcode. So what do we call these like 3-letter names that we give to instructions? So this is the load instruction, load to the accumulator.
Mnemonics.
Yeah, mnemonics. Excellent answer, Anonymous 5. I've got to keep track of where I got up to as well. Anonymous 5, give me a good answer there. So that's the opcode. So that assembly language, that mnemonic, basically says, oh, that's 001100, whatever it is. Okay? This bit is the addressing mode. So this represents the bits that are set for the addressing mode. This bit is the data of the operand.
Would it be like, would they use a symbol in the test? Or
Now, the terrible thing, the exam board have decided to use Little Man Computer for their assembly language stuff.
Yeah.
It uses one addressing mode. So whenever you write things in Little Man Computer, there is only one addressing mode. So there isn't this one, and there isn't the other 2. So what they have done is that on one question they made up some addressing mode symbols. So they use I think they use an ampersand, and they gave you an instruction and they said, right, this is what ends up loading in the accumulator, work out what the addressing mode was. So it's like, oh, for 1 mark, it was like, blimey, there's 5 marks worth of thinking to get that, and they only gave 1 mark to it. So it's a bit, you can work it out, and we'll look at that instruction, but it threw me a little bit because that was the first year through, and it was a bit blind what we were going to get expected to answer questions on. But yeah, so they will make things up. And you can see, I program in Z80, 6502, 6809 assembly language, and 68000 assembly language, and they all use slightly different notation anyway. So what I'm putting down here, so I've used a hash, okay, but this might not mean the same thing in a specific assembly language. We're abstracting a little bit, remember? And actually, if you want an example of abstraction, a mnemonic's an abstraction, isn't it? We're removing detail and concentrating on what matters, being able to recognize the instruction, not what it represents as a machine code. Okay, so that's that structure of a machine code instruction, but seen as an assembly language format. Okay, right, so what I'm saying this addressing mode represents is what we call immediate. So this is immediate addressing. Okay, now what immediate addressing instructs the control unit to do is to say, you know that data that's in the operand, that is the information we want. Okay, so this instruction, which I've now nibbled the bottom of, this instruction says load the value 6 and place it in the accumulator. Right, to execute this instruction, which is at memory address 150, so if I just put address there, what do I need to set the state of the PC to? What do I need to alter in the PC so that we can execute this instruction?
So set the program counter.
Excellent. Anonymous 1.
These two.
Oh, Anonymous 2, sorry. I always get you two mixed up. Yeah, I know I'm stupid. I can't help it. I can't help it. I'm easily amused. Right. So if we don't need to worry about any other registers because they're all going to get overwritten during the fetch execute cycle. So the one that matters is the PC. The PC says that's where you get your next instruction from. So if I want to execute instructions from address 150, that's what needs to be in the PC. Right, okay, so step 1 of the fetch execute cycle was what?
Give you the value in the PC.
Yes, do a transfer from the program counter into the MAR. Why is it going in the MAR? Right, correct, Anonymous 1. No, 4. Anonymous 4.
Wasn't it?
He's one.
He's one.
I was one.
I thought green.
All right,
But you can consider actually.
don't say people's names.
Was one.
Anonymous 6.
He's five.
Is he?
Why is me?
I don't think Andre's ever.
It's hard, isn't it? It's hard, people. Right. So, the memory address register, if we want to access a location in main store, main memory, we need to place its address in the memory address register. And this is crucial. You don't remember the fetch execute cycle. What you remember is the purpose of the registers, what their function is. Remember, the registers don't do anything. They hold data for a purpose. That's what you will get asked about. Okay, so we want to access an instruction that's at memory address 150. So in order to do that, we need to set the MAR up with that value. So that's why we do the transfer. Okay, next step is to do what? So I'm just going to, in my little trace table, I'm going to put, right, okay, look, 150's gone into the MAR. Right, what's step 2 the fetch X? Anyone from the higher order anonymous numbers on the left hand side want to chip in? I know you do. What is the next step? So we transferred program counter to the memory address register. So we selected that memory location. What does the control unit do next?
It does not get transferred to the MDR.
Correct, Anonymous 7. Am I up to 7? You're the higher order. You can treat that as a compliment if you want. Right, so we get the control unit goes, right, transfer, do a read from main store. So remember, we can write that quite nicely as main store and then treat it like an array because effectively memory is treated like an array. Although it's not linear access, it's random access. And that arrives at the memory data register. So this part of the fetch execute cycle is the same every time. Okay, this does not change. So we end up in the MDR. Now, bearing in mind it's a number, but I'm going to leave it in assembly format so we can follow it easier. So LDA #6. What's the next step? So it's arrived at the CPU, this instruction. What do we need to do with it immediately? Anyone? Yeah, and you'll see why in a minute. We need to copy it. The control unit goes, I've just brought something from memory. I was at the start of the fetch execute cycle. I'll assume it is an instruction. It could be data. If we pointed the program count in the wrong place, it could be a piece of data. Okay? But that gives us lots of advantages. We can actually write instructions into memory and execute them. So you can write self-modifying code. So step 3 is to say, right, we assume what we've got in the MDR is an instruction, copy it to the current instruction register. So in our little trace table, we do LDA #6. Okay, at this point, we then say decode, work out what the instruction is. So we do a decode. So we look up the opcode in our big book of opcodes. The CPU's got a Ladybird book of opcodes that it has a big thumb through. Okay, and it works out what it is. And it says, right, I've got to load something to the accumulator. What's the other thing that happens when we do the decode?
Increment.
Yes. As soon as we've decoded an instruction, we know how much space it occupies in memory. So we can then say, well, we want to move the program counter to the next instruction. So it might be, in reality, an instruction that occupies 1 byte. So we just add 1. It might be an instruction that occupies 2 bytes. So we add 2. It might be one that occupies 3 or 4 or 5 bytes, depending on what the instruction is. So it isn't until we've decoded that we can really work out where the next instruction is. We abstract this quite a lot, and we would just say add 1. All right? Because we can think, we're not looking at any particular instruction format. So in an abstract way, we're going to say, right, well, the program counter goes to 151. So it's pointing at the next instruction. And this is what Little Man Computer does. That's an abstraction as well. Right, so step 5, increment PC. Right, so that phase, the fetch and the decode, is identical every single time. So if you had to give jobs to people, don't ever put your hand up if someone says, who wants to do the fetch and decode bit? Because you'll be doing the same thing billions of times a second. It's the execute phase that's the interesting bit. So we would write in our general fetch execute cycle this, execute. But we're now going to look at what that actually means in practice. Okay, so we've decoded. And we've said, right, we've got an addressing mode. We're calling it immediate. Immediate means that is the data that we want for our instruction. Where is that data currently stored? In that CPU. Yeah, current instruction register. Don't say MDR. That's what we used to say at GCSE. It's in the current instruction register. That's where the decode operation actually happens. Okay? So we need to get that 6 into the accumulator. So we can write this as a transfer. We can say, transfer the data, which means the data part of the operand, to the accumulator. We don't have to do any more work. We're actually physically performing the execution. So we're doing the task. Transfer 6 to the accumulator. So the accumulator ends up with a 6 in it. What's the final step?
Check interrupt.
Yeah, check for interrupts. When I did this with the other class, I ended up writing just int by the end of this. Because I got sick of writing check for interrupts. Because it's, look at it, how long is that? Right, check for interrupts. Now, if we want to think about this immediate addressing in a more abstract way, when we're doing high-level language programming, this is an equivalent of having a variable called ACC and writing a piece of code like that. So ACC equals 6. Okay? How could we describe the 6? What could you use to describe 6 in this context?
Data inside the operand.
No, in this context, in this high-level language concept. Yes, anonymous 6, 5, 4. 5.
Is that an address to the, no.
No, it's literally not an address. Right, think of it this way. Every time I run that program, what value gets loaded into the accumulator?
6.
Right, so what does that tell you about the 6?
It's loaded into the accumulator.
Static.
5.
It's a constant.
It's a constant, thank you. It's constant. But it's a special type of constant. We need to say literal constant. So immediate addressing is like providing a literal constant. And the reason it's literal is because it's embedded in the instruction. It does not change. So we've got LDA #6. Every time I execute that instruction, it's always going to be a 6 that gets loaded. I've literally specified a constant value. And we do this all the time in high-level languages, don't we? Go on.
Why do we have to say literal? Is there like a different?
No, because that's what it is. It's literally a constant. It's not a constant that you've given a name to. It's a literal. It is there. As it is, it's a constant. It's the same thing when we're programming in a high-level language, and you put text in double quotes. You're actually providing a literal string, and if you get error messages surrounding it, it will say literal string. But yeah, it's a literal string. You're saying that is the string. That you can see is the string. It's literally a string. This is literally the constant 6. Because you've got, it's that problem of, normally when we talk about a constant, we mean a named value that doesn't change, don't we? And that makes your code more readable. So literal constants aren't the same as constants. Because literal constants can make your code unreadable. If you use the value 10 in 15 places in your code when it was all actually meant to be the same thing, then that would be bad practice. But still a literal constant. Right, so that's an equivalent of, so immediate addressing is the equivalent of doing a literal content. And you can see that the execution is just one step. So these are going to be the quickest sort of operations that the CPU can execute. Because all the data it needed to get on came when it fetched the instruction. There's usually, when you're writing code involving these, because of the instruction length, there's usually a limit to how big these numbers can be. Okay, in Motorola 68000, that uses a 16-bit instruction length, the immediate modes, there was only 4 bits. No, there was 5 bits, so you could have a number that was either minus 16 to 15. That's all you could have. But it was handy if you just needed to initialize values. You know, you wanted something to be 1, so you could use immediate addressing, and it was quick. Okay, right. Anyone got any other questions about immediate? Immediate is the easiest one to understand. It's there. It's immediately available, the data. That's how you need to think about it. Right, so let's move on. So I'm going to rub off. I'm going to leave the first 6 steps because they're identical. I'm going to rub off that. And I'm going to empty my contents of my registers. But the only thing I need to actually overwrite is the program counter each time. Right, so let's look at the next addressing mode. Now this is the one that Little Man Computer does. So we would have LDA6, and this is called direct addressing. And this is where the data in the operand is treated as a memory location where the data is. Okay, so in this case, this is the high-level language equivalent of writing ACC equals 6, 6 being a variable. So we look it up. Okay, so this is the equivalent of a variable. Remember, all a variable is a name we give to a memory location, isn't it? So that's what we're providing here. But when we're writing in machine code, we specify the memory location, that's all. Unless we use symbolic addresses. Okay? Right, so this is like a variable, if you want to think of a higher level language. Again, let's reset the PC to 150. And let's follow through the execution. So, step 1. Program counter. Transfer it to the ML. We want to read from location 150, so we need to select that location. We then do a read operation. So what bus does the data come along? There's a clue in the words. What bus does the data come along? Data bus. So we chug along the data bus at whatever speed. And remember, the CPU doesn't know where in memory this is. It doesn't know whether it's coming from the cache. It certainly doesn't know whether it's level 1, level 2, level 3, or RAM, or ROM. There's a memory controller that takes that address and does the work. The CPU is agnostic. It doesn't know. It just says, there's something coming on the bus. Okay? Doesn't know where the bus has come from. So we arrive at the MDR with LDA6. Remember, that is a number. We're just looking at it as an assembly language format. Step 3, assume it's an instruction. Copy it over to the current instruction register. Okay, we decode it and we go, oh, it's another load instruction. But this time it looks at the addressing mode and goes, it's direct addressing. That means I haven't actually got the data yet. What I've got is an address. So we increment our PC. Now we've worked that out. So we increment the PC and we say, okay, I've got the location of the data. I need to now access that location. So where should we put the 6? So in order to get this execution happening, where do I need to put the 6?
MAR.
The MAR, correct. Anytime you want to access memory, the MAR is your friend. So I am going to transfer the data this time to the MAR. That's my first step. But that doesn't give me the data, does it? What do I need to do next? Yeah, I need to do a read. I need to do a fetch. So one thing that you've got to realise, fetch, decode, execute isn't the whole story. There may be more fetches required, which is what we're seeing now. So we're now going to do a fetch. So we're going to read, and I'm going to put the specific value of the MAR in. So I've transferred the 6 to the MAR. So I'm going to say, from location 6, transfer that value and hold it in the MDR. Now, at this point, we have fetched the data that we need for our instruction. So our instruction, we decoded it and it said load to the accumulator. So we can now transfer that value to the accumulator. So what transfer are we wanting to happen? What register to what?
Is it MDR to accumulator?
Yeah. So we say transfer. So the control unit is kicking signals down the control bus saying, right, okay, MDR, you open yourself. Accumulator, get ready for a value to flow along the internal data bus, the one that's on the CPU die. So that this happens. At that point, we've finished executing. So we do our final check for interrupts. But can you see, when we did the immediate mode instruction, there was just one step to the execute. This one's now got 3. And this is what makes instructions take different amounts of time. We're only looking at 4 simple addressing mode formats. In reality, most CPUs have got more. And one thing that made different CPUs popular for building systems as opposed to others were the flexibilities for the developers. You know, if you look at something like the Z80, it's got a lot of registers, okay, and it's one of its competitor chips was the Motorola 6809, which didn't have as many registers, but it had some great addressing modes that made it really powerful. So something that would take a few instructions in Z80, you could do in one instruction on a 6809. So there's pros and cons to all processors. It's nice working on different ones because it makes you think in different ways. And the code you produce has to have different solutions for different situations. Anyone got any questions about direct addressing? So that's the one that's like a variable. So the memory location of where data is. That's what Little Man Computer uses. Okay? Unfortunately, that is the only one that Little Man Computer uses, which is why when we did some programs and you wanted to like set the accumulator to 0, you couldn't just say LDA-0. You had to create a memory location, give it a name, put a 0 in it, and load from that memory location to set a 0. It's all a bit mad. So it's several steps, several bits of memory. Okay, the next one. Can anyone say what the next in level of complexity is? What's the next addressing mode? Indirect. Correct. Okay, so let's reset the CPU. I'm going to use 150 again. Right, it's got another name in direct addressing. And it really, the name comes from how it's mainly used. So I'm going to represent indirect addressing, and remember this is just my format. It's not any specific machine language format. I'm going to put it in brackets. But I'm not going to use 6, that's a stupid number. I'm going to use 153, which is less stupid than 6 in this context. Right, so I'm going to do some dots, and I'm going to put 153, and then I'm going to put 157 in there. I'm going to go 157, 43. So I've got a chunk of memory this time. The alternative name for indirect addressing is vectored. Vectored addressing. And it comes from interrupt vectors. Okay. What this addressing mode allows a hardware manufacturer to do is to specify a specific fixed location where the program counter will get set to in order to carry out a specific task when an interrupt occurs. Now let's think of this in a little bit more abstract level. If I press a key on the keyboard, I want the keyboard handler to activate and say, oh, I know how to do something with that. I'll take that data and I'll do whatever it is I need to do with it. Put it in a buffer, pass it on to the current application or whatever. Okay. If the keyboard interrupt handler had to be pre-known and pre-written, we wouldn't ever get anything to work. What if I plug in a fancy keyboard that needs its own routine? I would have no way of changing it. But what this sort of addressing system allows us to do is to say, you put your routine at that location. We will use that data at that location to go off to your routine. So when an interrupt occurs, what actually happens is that generates an interrupt vector that goes to a specific location and looks for the data that's there. That data can be changed. Yes, anonymous, 2. 1, anonymous 1. I'm always mixing you up.
Is that how ISRs work then?
That is exactly how interrupt service routines work. So a benefit of this to nefarious people is that if I want to insert my malicious code to scan the keyboard and capture everything the keyboard's doing, all I've got to do is overwrite, make a copy of the address that's in the interrupt vector location for the keyboard, keep a copy of it, put my address of my program so that my program gets executed. I do whatever nefarious things I want to do, and then what I'll remember to do is call the keyboard routine at the end. And then no one knows that I've just intercepted. Not good. So a great deal of work goes on stopping programs getting access to these things so they can override. It used to be a free-for-all. And one of the things that I used to enjoy doing was just like getting rid of the operating system completely on the computer, just having your own code there. That's how old school computers work. You'd go, oh, the operating system's using up a bit of memory, I'll have that myself. And bye-bye. It meant you had to write certain things that the operating system provided, but it is one of the old school tricks is to just bin off the operating system once your program's running. Unless you need specific functions that you can't be bothered to write yourself. Because some of them are horrible. Okay, so that's where the naming comes from. Let's see what this looks like in operation. So again, I'm going to keep all the fetch execute steps up to where we say execute, and we're going to look at how this is executed. So we've reset the PC to 150. So we're going to do step one. So I'll run through it a bit quicker this time. So PC to the MAR, because we want to select, turn the pen on it though. I want to select that location because I want to read the instruction there. Transfer to the MDR. So we end up in the MDR looking at it like an assembly language instruction is LDA 153. We assume it's an instruction, so it ends up in the current instruction register. So LDA 153. We decode it. We go, ooh, it's one of those interesting ones, indirect addressing. I haven't got my data. We increment the PC because we now know what the size of the instruction was. Right, so the control unit goes, right, to order to execute this, I've got to get that data. So what I know that indirect addressing means that 153 is an address. So where's it logically going to put the 153? Yeah, MAI, it's an address. So we're going to say the data needs to transfer, so that's our first step, to the memory address register. Then what we're going to do, logically?
But would it be already in CIR at that point and then go back to the MAR? Or would it go straight to the MAR in the register?
No, I've just set up a value in the MAR. So what's the effect of putting the value in the MAR?
What's in that address set?
No. No. If I put a value in the MAR, what am I effectively causing to happen?
Another cycle?
No. I'm selecting a memory location. So I'm sending an instruction across the address bus, that number, that address, to say, select that memory location. Because I want to do something with that memory location. I want to read it. Okay? It doesn't do anything other than select a memory location. So I then can do a fetch. So I can say, okay, whatever is there. So at the minute, in the MAR is 153. So I'm going to say from location 153, fetch, bring it. Yes, everything arrives at the MDR because it's the buffer. It's the communication point, the holding point for data that's arriving or leaving. So that ends up in the MDR, 153. And you can see straight away that we've just obliterated the instruction. So if we were still thinking in GCSE mode, we haven't got our instruction anymore. And we're nowhere near getting ready to execute it yet. And we've lost it. We've got 153 in there, which actually might be another instruction. Whatever the 153 represents. Right, so we've done that transfer, but this is indirect addressing, so that isn't the data we want. That's an address. Okay? Oh, I've put what? No one spotted what I did wrong there. What's in 153?
153.
Yeah. Be careful, that is a really easy mistake to make. Okay, so at that memory location, when I did that I keep doing that today, was 157. So that's in the MDR. But that ain't the data we want. That's the address of the data. That's what this indirect addressing is. It doesn't go on infinitely, this is it. So we say, at a memory location, you will find an address. At that memory location, that's where your data is. So what do I need logically to do now? If my data is at address 157, what do I need to do in order to get hold of that data? Yeah, I need to transfer the 157 to the MAR. So and that data currently is in the MDR. So look how complicated this instruction is getting to execute. I've done 3 steps already and I still haven't got my data yet. So I'm not ready to do an execution. Right, what do I logically do next? So I've just selected a memory location, so what do I go for next?
Select the address.
No, that has selected an address. Putting something in the MAR sends a value down the memory address register.
Look at like the main store of that.
I don't look at it. You've got to use the right terminology. Fetch, read. Got to do another read. So I'm going to read from main store the address that's in the MAR, which is 157. Let me scroll that up a bit so you can see. Oh, I need to keep my thing on the screen. Right. Where is it going to arrive? MDR. What's going to arrive in the MDR? 43. Right. At this point, the control unit goes, thank you, I have now got the data. I can now actually perform the execution. So I've done 4 steps. That's actually included 2 further fetches. So in order to execute this instruction, in total I've fetched 3 times. This is why cache is really important. Because if I can increase the fetch speed, I will automatically increase execution of more complex instructions. Okay? If that has to go out to RAM, the CPU is idling, massively idling. So from the decode phase, it's done nothing but fetch stuff. So actually the execution unit's doing nothing. Sat there reading a book of choice. I don't know what it would read. Don't know. Anyone got any ideas what a CPU might read in a comedy way? Anyone thinking comedic?
How to be a human?
He said anything comedic.
Yeah, I did. Yeah, number 1, anonymous 1 or anonymous 2. Yeah, anonymous 2. I did say comedic. Yeah.
Oh, yeah.
So that, in general, that means that people would laugh when you said it. There you go. Right. Okay. So once we've got that data, we still got one more step. So we're doing the execution, which was to transfer the data to the accumulator, which is in the MDR, and we transferred to the accumulator. So we can now put the 43 in the accumulator. Why is that not drawing? I think it's too close to that other thing. If I was trying to select it, isn't it? So we put the 43 in there. So we can now we've finished executing, we can do our final step, which is our interrupt check. But can you see how much work the control unit had to do before it could execute the instructions? So compare that to the immediate, there was 4 extra steps involved, which actually involved data transfers. So data transfer speeds between memory and the CPU are critical. It is the major bottleneck we've got in CPUs, which is why we're trying to get cache bigger and bigger. But that's just like, you know, a snake eating its tail sort of thing. You can't just massively increase the cache. I mean, we've got huge caches, 16 megabytes of cache, which is nothing compared to how much main memory you've got when you've got like 32 gig of RAM. You're talking about 2,000th the size. But actually, for someone like me who's used to like 32 kilobyte computers, or working with computers that have got 900 bytes of memory, RAM, and 16K of ROM, it's like 16 mega cache. He's like, whoa, let me at it. But you don't get access, you don't get control of the cache like that because you've got the operating system running all sorts of interesting things. But yeah, so we can't just, it is the bottleneck. RAM just doesn't operate as fast as the CPU. Unfortunately. It's very fast. The fastest RAM that we've got is fast, but still don't keep up with the CPU, unfortunately. Okay. Right, so that was indirect addressing. What is the final one that we need to learn about? Yes, number 5.
Indexed addressing.
Indexed addressing. He said that like a robot. You did. You said that like, like if someone like, there's like a few YouTube channels where people,
You made him
they,
identify. Oh, I just didn't.
what?
Specify gender, can we? Data, isn't it? Can't do that. Refer to everyone as it. Anonymous doesn't have a gender, so.
No.
Yeah.
Exactly.
So I
Number
just
five's
said,
quite
hey,
cool. Instead of a number
yeah,
one
and-
is 5, I think a number 5 sounds
No,
better.
but we should.
Anonymous
It should be.
identifies
So
as
should be referring
Yeah,
to
well,
us
not
as
going.
it.
She's number 2.
I do in private.
Yeah, I think so. Number 1 they
Right. Okay. Let's scrub. Right.
Wow.
Indexed addressing.
So,
What's peculiar about indexed addressing? Right. All of these are about calculating what we technically call an effective address. Okay, so where is the data? It's 2-part. That's the key bit. So it's easy to identify compared to all the others. So index is 2 parts. What do we generally give these 2 names? The 2 parts?
Base value of
Base and offset. Okay, good. Right, so let's have an instruction. So again, this is going to be my format. There are loads of different formats for this. I'm going to use a different format to what I use with the other class, so just to keep it fresh. So I am going to put, well, I'm actually going to have to do 2 things. So I'm going to write a couple of instructions here.
How many lines is this going to be?
Not many.
4 lines left.
Oh, it's not going to be enough. Go over the page, go over the page.
You said it wouldn't be that many.
Well, it isn't. But I've got to put some data in as well. Right. So I've got 2 instructions. I'm going to do load to the accumulator again. But this time I am going to say, and I'm going to draw it like this. So I'm going to put brackets. I've got to think in my head what I'm doing here. 160. Okay, and I'm going to put some dots. And then at 160, I'm going to put my data. So I'm going to put 65, 66, and just to annoy, what number would you like to be?
11.
Ooh. And just to annoy 11, I'm going to put 4 pieces of data. Right, okay. So let's just have a look at this. So index addressing, we have a base value and an offset. And the effective address is base plus offset. Depending on the CPU, they work in different ways. Generally, an index register is set up and that value is changed. It's incremented. The base value is generally where the data starts, where it resides. So, what I've created here is what we call a null terminated string. So, if I was to look at this data as ASCII values, it would be A, B, C, with a 0 at the end, the actual number 0. Okay? It's how we used to do strings. So, you put a 0 at the end because there isn't a character for 0. It's actually, if you look at the ASCII spec, it's called null. Okay, null terminated string. So what we do is we have the base is 160. So I've specified that here in this index mode. And because I want to access the first location and then I might access the next and the next and the next, I've initialized the X register to 0. This is why things start at 0. So when we're accessing arrays, the first item is at 0. It's the index register's value. Okay? That's why. So the calculation, so the CPU's got to do, the control unit's got to do a calculation. It's got to get hold of this base value and the offset value. So let's have a look and run through this instruction. So again, the fetch execute cycle up to stage 6 is identical. So we go PC to MAR, fetch. What happens into the MDR is LDX. So we've got a couple of instructions to do this time. Hash not. We're going to do this quick. I'm not going to run through it too fancy. Let me have to scroll that down a little bit. We assume it's an instruction, so we go in the current instruction register with that. So LDX hash 10. And then I decode it and I go, okay, yeah, it only takes up 1 unit of memory, so we can increment the PC. And then we say, right, okay, what addressing mode are we using?
Wait, why have you put 10? I'm confused now.
Oh, well, no, it's hash. Hash looks like that.
No, the next one.
Because I'm an idiot. But at least number 11 spotted, number 10 mistake there. Is that because you feel superior to 10?
Is that 10?
Oh, we can have endless fun with this, can't we? No, we can't. I think we juiced out on the fun ages ago. Right, good spot though, number 11. It's quicker to say number than anonymous.
Yeah.
And anonymous has got too many.
Ends.
Yeah, it's horrible word. Right, okay. Good spot. We're using immediate addressing, so we don't have to do any more fetching. So we just execute that by sticking the 0 not in the accumulator. We need to just keep our trace table with an X. Oh, it doesn't like drawing up near those icons. Right, so a 0 goes in the X. We've finished our fetch execute. We're going to start again. Okay, so we're going to load from 151. So that goes into the memory address register. We do our fetch. So in the MDR now is LDA X160. We assume it's an instruction, so we copy it to the CIR, which is now robbing my accumulator side. So I'll just do a straight line. If you use a transformation on it, it would be a straight line. I would challenge you to create the mathematical function to turn that curve into a straight line. I didn't think so. Right, okay, moving on. Right, we decode it. We work out how long it is so we can increment our PC. So we're ready for the next instruction in sequence. Right, okay, so we know it's index addressing. We know that we've got to add 2 values together. The control unit can't add values. What component in the CPU adds values? ALU. So we're going to bring in the ALU to do its magic. We tend to draw the ALU like this, like a V. So it has 2 inputs. Who cares? Right, so our 2 values are the X register, and if we look at the operand, 160. Okay, so 160 is still the data part. The addressing mode is specifying the X register. So we take those through the accumulator and we get, in this case, 160 because X was 0. Okay, so the control unit has passed that off to the ALU and said, oh, you do your maths on that for me. It then gets the effective address. So that is where the data is. So what are we going to do with the 160? Yeah, we are. So we're going to take that result. Now it isn't in the accumulator. It's not going into the accumulator. It's just a special hold location. So we're going to transfer from the ALU to the MAR. So we take the calculations just performed and we say, right, we'll dump that in the memory address register. We've selected that memory location.
Wait, I've got a question. So is X the offset and 160 is the base?
Yeah. So we've got a fixed base, which is just the memory location for where this string exists. Okay? Right, so we've done that. So logically, once we've selected a location, what are we going to do?
Put 65 in MDR.
Use the technical stuff. That's the outcome fetch, correct. So we do a transfer. Main store from 160, because that's what the MAR's got in it, and it arrives at the MDR. So we get 65 in the MDR. Okay, once we've got that, we have got the data we wanted to execute with. So we're going to move that to the accumulator because that's what this instruction was. So we go MDR to accumulator. And we end up with 65. Then we can do our final check for interrupts. So again, you can see that this time, the few steps. This one actually involved another component. So it wasn't just a control unit doing fetches. It went, oh, go off and do whatever you need to do. Okay? So there was multiple steps again. The speed at which index addressing works is one of the killers. You try and avoid using index addressing generally when you assemble language programming because you know it's going to take time. They're very useful and they allow you to access data in a structured way. So we can use this to access arrays, but you can also use it to access records. So sometimes what you do is you switch it around. You have a fixed base value that might be 5, and then an index register that points to the start of a record, and you increment that to the next record because you want to read the 6th item in a record. Okay? So index registers allow us to access arrays, which are the most efficient for, but you can also access records of data. So all these things that we use when we're high-level language programming, fundamentally, we're actually writing code that gets translated into things like this. On some CPUs, so on a 6809, it's got an X register, where it's IX and IY. Some of the instructions take longer if you use the Y register, not the X register as an index register. It's really weird. So you have to be really choosy as an assembly language programmer and try and maximize everything that you do. Okay, so that's the 4 addressing modes that we need to know about. So let me stop the vid there.